All right, hello. Welcome to Revolutionizing Fleet Electrification with Automated Load Management, a webinar hosted by the Mobility House. I'm Samantha Scheib, the moderator for today. In this webinar, our speakers will go over the basics of automated load management, or ALM for short, how to design and permit for an ALM at an EV site, and what the benefits are for implementing ALM in your next EV site. So this is Click Meeting. It's fairly easy to use. There's a chat. I'm going to be turning on a question and answer mode that should be on. And if you write a question in the chat and you add a question mark, it will show up. So our speakers today are Elizabeth Hughes from the Mobility House, Alan Sly from P2S Inc., and Arup Bharat from Itron. Elizabeth Hughes is a sales engineer here at the Mobility House and specializes in integrating ALM technology into large EV locations. She's focused on helping customers understand the unique advantages of the Mobility House's products and how they address challenges. Her prior experience at General Electric, specifically in Power Grid Division, provided her with a comprehensive view of distribution concepts. Notably, Elizabeth actively contributes to the Canadian Standard Committee for ALM Technology and was a contributor to the Mobility House's ALM Technology Guide. Alan Sly is an electrical engineer and studio leader at P2S's San Diego office. Alan has almost a decade of design experience exclusively gained at P2S. He specializes in diverse markets, including commercial, higher education, K-12, healthcare, and federal projects. And Arup Bharat is a senior project manager, EV infrastructure LOB at Itron, and he's a seasoned clean tech professional with over 20 years of experience in green tech, smart grid, and software sectors. As a senior product manager at Itron, he develops EV fleet solutions, leverages EV as DER assets for grid edge ecosystems, and he holds patents in PV power electronics and contributes to the IEEE 1547.3. I'm going to now hand over the floor to Elizabeth.
Thanks, Sam. Okay, today, everyone, I will be covering the basics of automated load management. I will be covering what problems it solves, what it is, what you need to do in order to use it, and how it affects site design. But first, I want to set the stage onto why automated load management is so important. As we all know, we're experiencing a shift towards the electrification of transportation. And this shift means more and more fleets are going to need more and more power. But all of this is happening at the same time that there is a shortage on the critical grid components that are going to be used to get these sites more power. And that's where the stark reality comes in, is that these grid upgrades that are easily triggered can cost over a year in unexpected project lead time delays, according to the Center for Sustainable Energy. And if you have to pay for them, they can cost you upwards of $500,000. Now, on the right side of the screen, there is an example site that I'm going to be using throughout the rest of the presentation to cover various topics within ALM. For this example site, our customer wants to install 4 150 kW chargers on a connection that is rated to 500 kW. For those electrical engineers in the audience, I'm going to assume a power factor of 1. And for those not electrical engineers in the office, don't worry, I've done the math for us, right? So those 4 150 kW chargers are going to be an additional 600 kW of new load onto our site, and that 500 kW connection is going to be downrated to 80% because EVs are considered continuous in the National Electrical Code. More on that later. So really, we get to the problem really simply, and that's we want to install more new load than we actually have space for. So if we weren't going to use ALM for this site, we have 3 options. All of these options have varying degrees of added project expense, delay, downsizing, or just other suboptimal features. The first is, of course, we could wait and pay for that grid upgrade, right? So grid equipment is at the distribution level, generally has a linear relationship between its size and its cost and the time it takes to install it. So obviously, the larger that grid upgrade is going to be, the more it's going to cost you. Our second option is we can install fewer chargers. And the question is, okay, how many chargers can we install? Well, we need to make sure the total nameplate capacity of the chargers is below that existing power limit. And so in our example site's case, that's going to be 2 chargers. It's 2 times 150 equals 300 kW, which is lower than our 400 kW limit. Now we can't fit 3 because that would that total would be 450 kW above our 400 kW connection limit. Obviously, installing only half the chargers is going to affect the operations of our customer site and is possibly going to require them to have to physically move around vehicles, or it's going to affect the duty cycle that those vehicles can operate. Our final option here is we could derate the chargers. Derating is when you use software to set a fixed max cap of power that these chargers are allowed to use. Generally, what you do is you take the amount of power left on that site, so that 400 kW, and you split it equally amongst the chargers. So we're going to get each charger a max cap of 100 kW. There's a couple problems with this, though. The first is that you paid for that full 150 nameplate capacity of that charger. The second is that this sort of cap doesn't really take into consideration any dynamics changing site conditions, such as the one to prioritize one charger over another. And finally, not all the power is used on the site unless all of the chargers are plugged in. So for my little graphic down here, we can see only 3 of the chargers are plugged in, meaning we are effectively losing 25% of the available site power capacity when the site is already power constrained. So I've talked a lot about, what are the problems that automatic load management solves, and a lot about what are the alternatives. Let's dive into what it actually is. Automated load management is the use of technology to control charging loads such that it stays below a safe limit. And because we're keeping it below that safe limit, we're allowed to install chargers that have a total nameplate capacity that is greater than the rating of the current capacity connection. And by keeping it below that safe limit, we are allowed to either avoid, reduce, or prolong grid upgrades. I want to dive a little bit more into each of these 3 things. When we talk about avoiding grid upgrades entirely, generally we're really close to the power that we need, but we're not just quite there, so we can use ALM to skip it entirely. The second, reducing it, ALM could be used to say, take the need of a 1 megawatt connection down to a 0.5 megawatt connection, right? Practically or linearly reducing the cost of that grid upgrade in half. And then finally, we could prolong the need for grid upgrades. This is really important, especially when we have fleets that are phasing in their adoption of electric vehicles. So we could imagine a fleet that has 4 phases, 25 vehicles each, and we're going to split those phases 2 years. So first phase, and then second phase, and then third phase, etc. Now, we could usually that first 25 vehicles will trigger a site upgrade, but if we're using ALM, we could buy that extra 2 years to allow the utilities to install the appropriately sized grid equipment so that by the time we get to the second, third, and fourth phase, we already have the grid equipment that we need. But you still are able to keep your project schedule going, and we're still able to get those first 25 vehicles at that site. Now, you can get all of this done if you do 3 things. The first is it's necessary to talk to the relevant parties. You need to talk to your authority having jurisdiction, as they are in control of the permitting process. You need to talk to your electrical contractor so they can factor in ALM to your site design. And you also need to let your utility know that you're thinking about doing ALM. The second is you need to run simulations. ALM is not a magic bullet. It cannot make more power randomly appear. So instead, we want to see how an ALM solution will affect the operations of your fleet. For example, if a fleet really needs to charge at 100% all the time, then ALM is not going to be the solution for you. But generally, that's not the case with most fleets. And so running simulations are really going to help you figure out what exactly is the best for you. And finally, from a technical perspective, we need to make sure that the EMS set point, the technical NEC term for that safe limit I described earlier, is set appropriately. So to give you more of an idea of what I mean by that, let's go back to our example site. On our connection, as previously described, we have 400 kW worth of space. And so we're going to set that EMS set point to 400 kW or lower because we have an ALM capable charge management solution, Charge Pilot in this case, but there are others. And so we're allowed to install all of the chargers without any upgrade required. If we look over to the graph on the white side of the screen, we can see how this differs from the derating I talked about earlier. In this situation, power is optimally shared between all of the chargers, even when not all the chargers are in use. For example, we see here that charger number 1 and charger number 2 are each using 150 kW, while charger number 3 is using the rest of the 400, it's using 100 kW, while charger number 4 is not using any. So I've talked a little bit about that ALM affects how equipment is rated, and on the screen here for you guys, I have the generalized equation on how you go about rating equipment. And really, there's only two main variables. Generally, the first variable is max load. You're going to take all of the load on your circuit, and then you're going to multiply that by a safety factor. Traditionally, the safety factor is about 125%, because it is related to the continuous rating of various pieces of grid equipment on your site. A really good example of this is most circuit breakers are rated to 80%. The inverse of that is 125%, so that's how we get the safety factor. And then, of course, we get our equipment size or our rating. ALM affects this equation by having you swap out the variable in blue. So instead of using max load, we're going to use instead the EMS set point, which is generally lower. And therefore, since we lowered one of the variables, we're going to see a decrease in equipment size. And of course, we're going to see that decrease in the cost of our grid equipment as well. Now, where do you go about finding if you're allowed to do ALM? That's the National Electrical Code. The National Electrical Code is a set of requirements for the design, installation, and operation of electrical equipment in the United States. It's vast and covers a lot of things. It covers connections, circuit protection, and in ALM's case, it covers the rules for how you go about rating equipment. There's a new version of it that comes out every 3 years. So the current version is 2023. And then the states have the opportunities to go and adopt that code as they want, right? So there's a patchwork of different versions of the NEC that are actually in effect across the nation. For example, we have states like Oregon that just adopted the 2023 code. We have New York on 2017, and we have Kansas down there at 2008 NEC. Now this matters because the NEC first allows ALM in 2014, and it's called ALM from 2014 to 2020. In 2023, it changes its name to an energy management system. All of the rules are still the same, but it's just good to point out that it shifts from section 625.42 to some of it living in 750.30. There might also be local rules that apply to the application and site design of ALM. So it's important to also contact your local authority having jurisdiction and your local utility to see if there's any other specific rules that might apply. Now, the Mobility House has installed ALM projects across the country, but I've picked out one for you guys to look at right here. It's a transit in California called Long Beach Transit. And at this site, we're powering 20 buses using 10 chargers. And of course, we're not derating any of the chargers because we're using ALM. On this site, we have 1.8 megawatts of charging capacity installed, where the existing connection can only handle 1.1 megawatts of capacity. So wrapping it all up, I know I've covered a lot, but I want to really highlight 4 key things. The first is that ALM regulates the amount of power that's used below a safe limit. It helps install EV sites by avoiding, reducing, or prolonging the need for grid upgrades. It affects the sizing of equipment needed and therefore affects your permitting process. And finally, you need to talk to your authority having jurisdiction, your electrical contractor, utility, and your charge management system provider ahead of time. And with that, I'm going to pass it over to Alan.
Thank you.
Yeah, you're good.
Good to go? Thank you.
Yep.
All right. Appreciate the patience there. Today, I'm going to be discussing a few topics surrounding, in general, electric vehicle supply equipment, the design and infrastructure of electric vehicles related to that Long Beach Transit project Elizabeth just highlighted, their implementation, including challenges, benefits, and lessons learned. So let's get into it. So first, taking a step back, why would we go electric? Many reasons: sustainability, community, and environment. The use of electric vehicles for individuals and businesses offers many benefits. Electric vehicles have no emissions, which would lead to improved air quality, which is a particular concern in Long Beach, with the Port of Long Beach out there. In some studies, it's shown even the air inside of a standard fuel-burning bus can be worse than the outside environment. So all the more reason to go towards electric vehicles. Electric vehicles are less noisy than combustion engines, which improves the quality of life for individuals using the bus and located around traffic routes. Some electric vehicles can be even treated like a battery storage system and provide a mobile means of power for tools, equipment, lighting. You can charge when energy rates are low versus charging when energy rates are high, and use that to your advantage. Depending on the size of the battery in your vehicle, you could power a house up to 3 days. And then you can even make arguments that electric vehicles promote economic development, where you're installing these in public and urban communities. People will tend to spend a bit more time there as they're charging their vehicles versus traditional fueling. Allows for opportunities to explore nearby businesses, restaurants, shops, and sort of just promote the community as a whole. Also, the cost of ownership is traditionally lower over the full life of the bus or of the electric vehicle. But there is a caveat that you need to take into account when you're charging your bus for taking advantage of those lower fuel costs and charging them during low demand times. Electric vehicles also contain fewer moving parts and systems than standard vehicles, including lack of engine oil, spark plugs, air filters, and transmissions. So without these components, it's easier to maintain and therefore reduce the costs to maintain. And there's also tax credits and incentives still for purchasing electric vehicles for individuals up to $7,500, and then commercial vehicles up to $40,000. There are some specifics to these, so make sure you look into those if you're considering purchasing an electric vehicle. So there are some challenges, however, to implementing electric vehicles. First and foremost, the upfront costs. Electric vehicles are traditionally more expensive than a standard vehicle, sometimes twice as expensive. Charging infrastructure is a huge component of implementing electric vehicles. Not only do you need to buy the chargers themselves, but you need to ensure that your electrical system is adequately sized to support the charging. As Elizabeth touched on, the automated load management can help, push off these upgrades or reduce or remove these upgrades entirely. And we'll touch more on that in a bit. And as I touched on before, the cost of operating the vehicle is highly dependent on where you charge it, what time you're charging it. Electricity rates vary pretty widely across the country. So individuals and business owners should try to fully understand, the utility impacts of using the electric vehicle and understanding when the best times to charge are and to plan their routes accordingly. Also on planning, with a new type of bus system and a new fuel, you'd need to probably establish different routes, different charging stations along your routes, and that could come with its own set of challenges for the administration. So now we'll get into just some EV charger basics. From the National Electrical Code, Article 625, their definition of an electric vehicle charging system electric vehicle supply equipment, EVSE, is the conductors, including grounded, ungrounded, and equipment grounding conductors, the electric vehicle connectors, attachment plugs, and all fittings from A to Z between your source of power and the electric vehicle. We're still on the 2020 NEC code in California where I do my projects, so I was not aware of the shift to Article 700 that she mentioned in 2023, but I'm sure I'll run into that in 2 years. But one particular part in the code there, 62542, is on the rating of the equipment. And so it states, equipment shall have sufficient rating to supply the load served. Electric vehicle charging loads shall be considered to be continuous loads for the purpose of this article, which Elizabeth touched on earlier with the 80%. And then it also mentions where an automatic load management system is used, the maximum equipment load on a service and feeder shall be the maximum load permitted by the automatic load management system. So it's, adjusting that system and control to meet your minimum demands and fall within the capacity threshold of your electrical service. Just a quick diagram on the right, there's 3 basic types of chargers. Level 1 is kind of your standard residential use, 120 volt outlets. It's going to typically be longer charge times, but that's where vehicles are parked for a fair amount of time overnight typically, and so they can account for and accommodate those longer charge times. And then we have level 2, which is commercial and residential use, usually a 240 volt outlet, much faster charge times. And then there's level 3 DC fast chargers, which will use a 480 volt 3-phase input, typically only for commercial use unless you have some means to provide that at your own house. And that'll be much faster charging for fleets and commercial businesses. I also wanted to touch on just a small part of the California code requirements. Title 24, Part 11, known as Cal Green, actually requires us to provide EV capable and in some cases full EV charging equipment on new construction projects. So EV capable is defined as having infrastructure installed, basically a panel board that is sized appropriately with a raceway nearby where you're going to install that charger. It has some specifics on the size, needing to be at least 40 amps, 40 amp circuit, and providing 30 amps of power. And then this is all dependent on the number of parking spaces that you have planned for your project. So as you can see, as the number of parking spaces increases, the number of required EV capable spaces increases, and then also in turn, spaces you need to actually install EV chargers. And so I think it looks here that, let's say 26, for example, if you have on your project, you'll need to provide a panel that can serve 8 separate circuits for 8 separate EV chargers. And then you would actually need to install 2 chargers within those 8 seats. And now we'll get into the specifics of the Long Beach Transit project. So here's sort of just a quick overview of the project timeline: design, permitting, construction, and commissioning. Design, of course, we got to deal with existing conditions. There's an R&D phase where we're looking at the types of products that we're using. In our case, this was when we got with a mobility house and met with them to understand, the nuances of the automated load management system, what types of information we needed to show on the drawings, the specifications that we needed to include, and the details for that. Then once you put the drawings together, there's a submittal to the AHJ. They'll provide comments. We need to respond to them. And then, of course, you need to deal with plan check fees. Then gets to the fun part, the construction. Contractor working on equipment procurement. This particular project was done during COVID, so there were a few challenges with equipment procurement and scheduling, which we'll touch on later. And then commissioning at the end of the system once it's installed to test it and ensure performances are within project parameters. So getting a little bit more into the design of the system, the scope of work here was to install 10 bus charging cabinets for 20 buses. This particular setup had sort of one cabinet to feed 2 chargers and then 1 charger per bus. And so the charging cabinet could modulate, how much power it needed to provide to each charger, depending on whether or not the bus was there and the schedule of the bus. Also in the scope of work, provide communications equipment for that charge management system, including all the devices, fiber, media, conversion devices. And then there was existing communications that we needed to tie into with that client. There was also a small amount of lighting that we needed to provide for the project, just so that the buses could pull in safely to the chargers at night. And also a few convenience receptacles along the charging path, just in case anybody needs an outlet for maintenance reasons. And here you can see a diagram of the single line diagram showing our feeders to all of the charging equipment. We have 2 meters within the board that are metering each of those charging cabinets, and using that with the load management system to ensure that the system's operating properly. This is a bit more on the specific charge management system itself. So here's a network diagram sort of showing all of the communication cables going to each of the charging cabinets and then each of the columns. We had a cabinet that sort of housed all of these charge components, the power supply, controller, an internet modem so it could talk back to the management system, and then a network switch for the communications. This is a shot of the meter that we used within the board. It's capable of, I think, 8 separate 3-phase loads, and so we needed 2 of these to accommodate all of the chargers that we had for this project. And then we get into the permitting side of things. So this particular project was submitted to the city, particularly the city's Department of Development Services. You can see on the right here, the AHJ had made some specific comments on the calculations where we were showing essentially a max load of 1400 amps allowed for our 20 chargers. And in that case, it was 140 amps per charging cabinet. So our initial approach was to sort of put this calculation form here in a note describing the load management system. And then they just wanted further information on that, including cut sheets and description. So I do specifically remember having a conversation with that plan checker just about the load management system, what we were doing for the project, because it was one of the first times they had seen, or really was the first time they had seen that implemented on a project. And so it took a little bit of convincing that this system has been used in the past, and that it's, a listed operating system. And so once sharing the cut sheets and things like that, he was on board and approved our project ultimately. And then we get into construction. Construction went pretty smooth for this project, even given the COVID constraints we were dealing with, because this was phase 2 of a project that we also worked phase 1 on. So we were able to design it well and set ourselves up for fewer hiccups ran into during the design phase. This is actually a shot, I believe, of the phase 1 chargers on the right. And then this is a new switchboard we provided to serve our 10 cabinets. And then you can see at the top in the middle there was the load management cabinet that houses all of the communication components. After construction, we get to commissioning, which I was not fully involved in. P2S has a separate commissioning group that will deal with that. But from everything that I've gleaned from talking with that commissioning agent, things went smoothly and we're operating as intended. Yeah, so it was a successful project for us and for the client. And with that, ends my part of the presentation. I think we will transition to Arup.
Thank you, Alan. Thank you, Elizabeth. I hope everyone can hear me. Thanks for giving a very insightful look into the project side, the demand side of the ALM proposition here. As we can see, ALM can be a very important ingredient in deployment of EV charging equipment, supply equipment, and for project success. I'm going to focus a little bit on the supply side of this equation. And that's really on how utilities look at electrification challenges and what ALM can mean for them from the supply side of being able to produce and provide and have adequate grid assets and grid supply available for electrification. I hope you can see my screen. If not, please raise a hand or mention something. Otherwise, I shall proceed. Okay. So just by way of introduction, Itron, we are a 40-year-old company, public company that has been squarely focused on providing technology solutions to utilities and cities. We support their critical infrastructure. We provide IoT-based solutions for cities and utilities to manage mostly the distribution side of their network. We are present globally in North America. We operate our forecasting services and support for 90% of the ISOs in the country, as well as sprinkling of national utilities, as you can see. Our journey really began with providing some of the early leadership around advanced metering infrastructure in this space, but has since evolved as utilities have evolved over the past 40 years. We have increasingly become more engaged in providing solutions for utilities at what we call the grid edge. As utility and complexity of managing utility networks have shifted from being more a centralized problem to more a distributed problem. As we have added more distributed generation, solar, battery storage, controllable loads, smart appliances, and now electric vehicles, utilities have had to evolve on how they manage, operate, plan for, and optimize their distribution networks. The intelligence is moving more towards the edge. And electric vehicles pose a very interesting problem to utilities. They are bidirectional, or can be. They are manageable and controllable, unlike several other loads that have proliferated. But they also tend to appear in very interesting fashions, localized in concentrated manners, and can significantly change the operation and the operational needs of a utility. So how does Itron and our utility partners look at this? This was saying, as utility conditions have changed, as their carbon neutral goals have accelerated, as they've started adding more renewables and storage, and now electric vehicles, there's been challenges to maintaining their reliability of electric supply, reliability of distribution management, and also reliability of being able to incorporate these increasingly new smart devices at the edge of the grid. The diagram that you see on your screen, the icons on the top, so the left 5 icons there are really typical assets that utilities have been able to manage, control, and have visibility into over the last 15 years, 20 years, through a variety of demand response programs, demand side management programs, from controllable thermostats to air conditioners. You probably have a controllable thermostat in your home, maybe even an air conditioner that participates in a utility emergency relief program. But then as the grid edge evolves by adding more electric vehicles, chargers, storage batteries, distributed generation, the challenge for the utilities is changing. The challenge is transforming from one of being centrally controlled and dispatched systems to having sufficient visibility at the grid edge to be able to manage and design their operations, to now being able to work in concert with the deployment of these resources to make sure that there is reliable and adequate supply and management of these resources. Of course, ALM is a key component of that equation, we feel. So Itron's approach has been to be able to provide that visibility and control to utilities of the distributed energy resources that are appearing in their territory. And we do that all the way from program design for utilities through implementation and execution, along with our partners such as Mobility House. Now, just to transition to why in this whole domain, why is fleet and fleet management even important to utilities? Well, what we're seeing is a tremendous uptake as a result of regulatory factors, availability of federal funding, state funding, and other factors that are driving an uptake in adoption of electric vehicles. Both Elizabeth and Alan spoke about that. In that domain, specifically, medium-duty and heavy-duty vehicles pose a specific challenge to utilities. Medium and heavy-duty vehicles, fleets, tend to be electrified in chunks, tend to be electrified, 5, 6, 10 buses at a time, maybe even more. They tend to be localized. They tend to be more depot charged, which means that the demand side of the equation changes significantly in a very localized fashion for utilities. All of a sudden, you have a huge need for a transformer upgrade or conductor upgrade or secondaries that need to be changed in order to accommodate a new fleet that suddenly appeared in their territory, or even gradually appeared on the territory, but it was not planned in their original infrastructure planning. We're seeing the influx of federal funding that is leveling the playfield, if you will, on electrification of fleets across the country. Today, fleets anywhere in the country can have equal access to federal funds to electrify. Hence, we're also seeing a big growth of fleet electrification in areas that were not originally planned for. And an unmanaged electric fleet can pose huge challenge for a utility. We've seen increase in peak load by 30%, possibly, with one depot electrification in utility territory. So what does this mean? It means utilities have to take a more surgical approach to enable their key customers, their territories to electrify their fleets and be able to catch up on the infrastructure side to be able to provide that demand sufficiently. Now, the two paths of doing that, one is to do infrastructure spending, which has sufficiently and has increased tremendously in the last 3 years for utilities across the nation. However, that requires significant amount of investment in both time as well as capital to do infrastructure upgrades. What utilities are increasingly more open to is adoption of innovative technologies, innovations such as advanced automated load management, ALM-based managed charging systems. And that's where we see a tremendous amount of innovation happening and acceptance of ALM technologies. Our approach to this challenge has been from the utility perspective and enabling the utility to understand the technology with our partners such as TMH, to deploy ALM-based technologies and making that part of the utility planning process. And we engage with utilities all the way from the grid infrastructure planning, impact studies, to acceptance of ALM-based solutions in part of the territory and be able to accommodate larger fleets. We typically take a phased approach to working with our utility customers to prepare them for EV deployment. We call it the walk, run, fly approach. Different utilities are at different stages of electrification within their territory. I'll focus more on the top two, right columns there on run and fly. Managed charging with basic ALM. Basic ALM meaning being able to do automated load management the way we discussed. Elizabeth and Alan, provided examples of. Is one that is currently available, is being deployed today, and we work with our utilities to really work with their key customers and key accounts to accommodate ALM-based deployments that would allow faster fleet electrification than infrastructure may allow at that point of time. But also in our roadmap, we are working with our partner, with Mobility House, on solutions that would allow utilities to do more advanced ALM, where not only will they be able to accommodate fleets that are larger than the infrastructure will allow, but also provide dynamic hosting capacity. So based on monitored transformer health, monitored distribution system health, be able to provide dynamic capacity to the fleet operator that will allow them to do better managed charging, a more enhanced managed charging. So just a view of the utility perspective around ALM and what we are doing in that domain. These are exciting times for EV growth, but there's a need for innovation and innovative technologies such as ALM for us to be able to not throttle that electrification transition. I'll stop with that so we can take some questions or any other discussion topics.
Yes, we do have a couple of questions, and thank you guys for presenting. So one of our first questions is, what kind of connectivity does ALM require? It could be managed platform necessary for ALM, or can it be implemented locally? That might be the best question for you, Elizabeth.
Yeah, sure. I'd be happy to talk about it. So a cloud management platform is absolutely not necessary for automated load management. In fact, there are a lot of benefits for automated load management to have a local component in its overall system architecture. Some of the benefits of localized management can be faster processing, right? More of the data is handled at that grid edge, as we've talked about. It allows for easier metering of various other on-site loads, right? Not all of our sites are as easy as that example site I gave. Some of them have uncontrolled building loads or loads that change throughout the day. And so connecting with on-site meters is really, really important. And finally, a local component to your ALM capable system will allow for more resiliency for things like internet connection loss, and it also provides for lower points of failure in a system whose really main job is to control and communicate with various on-site loads.
Okay, thank you so much. Getting in a couple of more questions. We have, what types of projects are most suitable to ALM applications? I think maybe Arup can answer this question.
Yeah, happy to take that, and please jump in, Alan and Elizabeth, too. Really, I mean, what we are seeing on fleet electrification side is, as you electrify fleets beyond just the first set of pilot electrification, the demand growth from the fleet electrification can be quite rapid. So I think ALM is a suitable solution to explore in a very large percentage of fleet electrification projects, specifically ones where you have a very aggressive electrification plan that may have started late, may not have been engaged with the utilities. In our case, where we work with utilities, we actually encourage them to explore the full gamut of managed charging solutions, including ALM, from the very beginning. Our utility customers put that on the table as really a strategy for most of their large customers. From a project perspective, I will ask Elizabeth and Alan to provide their perspective on where you've seen it being most suitable.
Yeah, I would say the projects I see where ALM is most suitable is to sites that have multiple different types of load, so EV load and uncontrolled load. That generally is a really good application for automated load management. Also, fleets that are using higher power and more chargers, obviously because ALM is tied to the need for power. Anytime you're going to have a fleet that rapidly needs a lot more power, that's going to be where you're going to want to look into your ALM solution. Generally, you're not going to need an ALM solution for 1 or 2 chargers, but as that scales, it's going to become more and more important in your planning process.
I just would reiterate what you two both just said. Typically for larger projects where you're having more chargers than just a handful, and I think that's a good point, Elizabeth, on clients that might have other uncontrolled loads within their building or what have you on site, that kind of limits the amount of EV charging that they can do outside of that. I think it's something that we're going to be implementing a lot so I think the demand for charging and for power from the utilities is probably exceeding their capabilities of providing it.
Just to add one more thing to that question there, I think when it comes to load management as an integral part of managed charging, I think the use cases that we are seeing are expanding. We've all heard of sort of the fourth Tesla problem, right? You have a subdivision or a neighborhood and you add a fourth Tesla, and that ends up overloading your transformer. I think the opportunity to use automated load management or load management as an integral part of any EV charging solution is going to grow. So the potential for ALM across a variety of uses, even use cases where you have a growth of electrification, transportation, EV electrification in a subdivision, not necessarily in a local area, is going to become a concern for grid operators. And ALM provides a very reasonable approach to that beyond reconductoring and changing out transformers or expensive infrastructure upgrades.
Thank you. I'm going to move on to the next question. And that is, do you have any information on current grid capacity overhead across the US?
Not sure if you have the ready answer to that, but I'm sure we can get back to we would get back with an answer on that question.
Okay. We also have, what is the difference between DERMS and versus ALM? And can DERMS have ALM algorithms capabilities package?
Yeah, I can address that. Others can jump in, please. So that's a great question. By definition, DERMS is a management system that allows you to manage a variety of distributed energy resources. It has been used at various levels of the grid, at the grid edge, at the distribution level, even at the grid level, to be able to provide visibility and control to grid operators of distributed energy resources, EVs being one such resource. ALM is more specific to managed charging solutions for EVs. ALMs can work in conjunction with DERMS, but do not require a DERMS system to be in place to be operational. You can have automated load management based on site constraints and an understanding of the requirements on site, independent of the other distributed energy resources that may be also residing on the same distribution grid. However, if you have a DERMS present, if utilities use DERMS or an aggregator uses DERMS, ALM can enhance the capabilities of that DERMS functionality. In terms of can DERMS, can ALM algorithms capabilities be packaged into DERMS? Technically speaking, it can. I think the electric code allows for it. However, the implementation of your ALM can heavily impact the reliability of that ALM, the functioning of that ALM. In our case, in Mobility House's case, it's a conscious decision to do that implementation locally that allows for much more reliable, much more dependable solutions than a cloud native one. But I'll let Elizabeth speak to that if she wants to.
Yeah, I think it goes back to, the original question about cloud management systems versus, your ability to locally look and react to power on site. Obviously, the farther removed the data processing is, and the more points of failures you introduce to a system, the more ways it can go wrong. And so when we're thinking about, working with oversubscribed panels, there is a strong preference to move that intelligence locally, to have hardwired connections, to put multiple redundant backups in place, so that this technology operates always as expected and in a safe and reliable manner.
It seems we have one more question, and if anyone wants to get any last-minute questions in, I see a few more coming in. And also, Sarah Daniels, your question about the models and sims, I think we're going to try to contact you separately in an email with some more information on that. And we will also share this webinar in an email to you guys in the next day or two as well. It's recorded. So we have a question that is, which utility companies in the Northeast are you currently working with related to ALM? So for the Mobility House, we have a few unannounced projects that we cannot speak about, but Elizabeth, I believe you have a project you can speak to, and up to Arup and Alan if there's projects they can speak about.
Yeah. So the project that I know we are allowed to speak to is NiceBus. So we're working with Con Edison at NiceBus for an ALM site.
None from me. We're primarily on the east or the west coast. Sorry.
I think from Itron's perspective, I can say, we work with most of the utilities in the Northeast, and ALM is a central part of the discussion. I'm not free to share names, but definitely this is a very integral part of what we offer to our utility customers, and we're working on some soon-to-be public announcements in the Northeast.
We have one final question. For the Long Beach Transit project, did the utility companies ask you to include hardware solution relays as part of your design? And I think that could be either Alan or Elizabeth have.
Yeah, I can chime in first. No, I don't think that they asked to include those specifics for relays. It was really the components of the charge management system, and just specifics for what we were determining the calculations to be kind of for each charger. I think that was a number that they were interested in, just to know that, you know, the sum of all 10 chargers would be less than that board rating.
Yeah, I would add to Alan that the utility was happy with the local components that are already inside the charge pilot system. So the local controller, our hardwired connections to all of the meters, and our hardwired connection to the chargers themselves, and of course the chargers being physically present as load on the site. So relays or any sort of other switching devices weren't necessary.
All right. I want to thank everybody for coming to the webinar and for all of our speakers for contributing. It's been really informative. We will send out an email that will have the recording, and I think we'll also include where you can access the Mobility House's white paper on ALM. So thank you guys so much, and we hope you attend our next webinar.
Thanks, everyone.
Thank you so much.
Thank you.